So this is a video for CVM 15 about calculating displacement from a velocity versus time graph. This is a tricky idea that may seem a little weird at first, but once you start to get the hang of it, it'll seem really powerful and cool. Here's the idea. The area enclosed by a velocity versus time graph and the v equals 0 reference point, usually the t-axis, can be used to calculate the displacement of an object during some time interval. The area enclosed by the velocity graph can be used to calculate the displacement. We'll show you how this works, and then we'll come back to these calculations of the area. We're actually going to use this example of the velocity graph that we got on the previous example. So we'll label this axis to match that. It'll be -1 and -2 for our velocity here, and +1 and +2. And this object is moving at a velocity of -1, -1, -1, and then stops and so on. So we'll see how this goes. This is going to be 5, this is going to be 10. So we're going to go out to 6 seconds at a velocity of -1. Then we're going to stop for 2 seconds, and then we'll continue in the positive direction for 2 more seconds at a velocity of +2 meters per second. Remember, our motion map for this looked like the following. We had it starting on at this mark, and it's moving 1 meter per second for 6 whole seconds. That means it's going to end up at 2. So this would be t equals 0 seconds. This would be 6 seconds. It pauses there for a moment until 8 seconds. And then it starts moving at 2 meters per second in the opposite direction. So it ends up moving up here. Then we can connect these arrows to say it's moving in the negative direction, and then stops and moves in the positive direction. So now we've got our motion map and we've got our velocity graph. The question is, how can we use the velocity graph directly without even looking at the motion map to figure out what the displacement is? Remember, this is x in units of, actually we'll say meters, and this is our negative direction, this is our positive direction. The idea here says, in order to calculate this area, we need to shade in a shape enclosed by the graph and then calculate the area of that shape. For example, if we see this shape right here, this rectangle, let's draw this again over here. And we've got this rectangle that is -1 meters per second on one side and 6 seconds on the other side. We've taken this shape that is made with the velocity graph line and the t-axis, and we put it up here, and we've asked ourselves, like, what is the area of that shape? If we want to figure out the area of this rectangle, we would do this calculation. We would say area equals -1 meters per second times 6 seconds, and that would equal -6 meters. The displacement, this is saying, is equal to that area. So let's check to see if this is true. If we've calculated this for the velocity graph from 0 to 6 meters, we would want to check, is that consistent with the motion map? Well, on the motion map, if we say, okay, how far does this thing go in 6 meters? We'll see it goes 1, 2, 3, 4, 5, 6. It starts at 4 meters and ends at -2. That looks like a displacement of -6 meters. So that's consistent. Let's try this other shape and see how it works. You may be wondering, like, why on earth are we calculating the area of things? We're going to get to that in a moment. We're going to see how that works. I just want to show you that it works to begin with. I'm going to copy over this shape, which is now 2 seconds wide and +2 meters per second high. we're going to calculate the area again. We're going to say that the area equals 2 meters per second times 2 seconds, which is equal to 4 meters. And we want to ask ourselves, is this consistent with what we see in the motion map? From 8 seconds to 10 seconds, how far does this thing go? Well, it starts at -2, 1, 2, 3, 4, and ends at 2. So that is also consistent. That displacement that's traveled is equal to the area again in this case. So I could remind myself of that. So the question is, why does this work? I'll include an explanation of that down here. We know that V average is equal to displacement over the time interval. If we wanted to get an equation similar to this that got displacement by itself, we could multiply both sides by, delta t. We are not changing the equation at all because we are multiplying both sides by delta t. But on this side, the delta t's cancel out, and we end up with V average times delta t equals delta x. That is, the average velocity times the time interval that we travel is equal to the displacement, the distance that we cover. When we are calculating the area of a shape, we can think of this as the width of a rectangle. That is, if we put a star by this, we can say there's a width here and there's a width here. We've seen those two widths. We're saying that delta t is the width of our rectangle. And we'll say that this, we want to think of this as the height. Let's put a heart on this, and we'll connect that to the height velocity up here and the height velocity up here. You may think this is kind of crazy. That is, that we're trying to use this idea of area to do these calculations, and we're thinking of a velocity as the height of a rectangle, or thinking of the time interval as the width of a rectangle. This is actually the foundation of something that you may have heard of called calculus. When we are doing this work in physics class, when we're calculating the area of shapes that we see, we are essentially doing calculus. So it won't be a huge part of this class because it is pretty difficult, but if it's kind of twisting your brain in knots a little bit, that's a good thing because it's a challenging idea, but that doesn't mean that we can't think about it and can't figure it out. So going forward, this will be something that you want to pay attention to as a technique that we can use when we see velocity graphs. If you see one of these shapes and you need to figure out how far something moves from one clock reading to another, you can do that by calculating the area enclosed by this shape, whether that's a negative area like this and gives you a negative displacement, or a positive area like this that gives you a positive displacement. If you're thinking like, actually let's make a note here. We're gonna say, watch out for quote unquote negative area from negative velocities. Coming from math, you might say the idea of negative area doesn't make any sense. Like, I refuse to use that. But if we think of math as a tool, we're seeing here that this idea of multiplying the length by the width is actually pretty handy. It gives us some useful answers here. It gave us two answers that were consistent with the motion map. So if this idea of negative area has a chance of being useful, we want to be open to looking for areas that we can use it.